All right, so in this problem we first encounter an equation to solve that has fractions in it on both sides of the equation. And so we're kind of working against two forces of mathematical mischief, right? On the one hand is all the algebra that you have to contend with to get that u isolated and by itself on one side of the equation. And the second force is the force of all the fraction arithmetic that bears down upon you when you look at a problem like this. So depending on your taste, you might decide to focus on the algebra first and worry about the fraction arithmetic along the way. Or we could tackle the fractions head on first and get rid of them, and then focus on algebra the rest of the way out. I happen to prefer the second approach, but your mileage may vary. So somebody that solved 5 and felt like they had a good opening strategy, what did you do to get started? Oh, all right. Awesome. Right. So this is the sort of divide and conquer approach. Divide meaning let's get rid of all the fractions, not have to worry about them anymore, and then do all the algebra. And we can get rid of the fractions using a technique that we call clearing denominators. Probably the most underrated, helpful technique that I know of in solving equations. And clearing denominators involves finding a number, a whole number, that I can multiply both sides of this equation by, and the result of multiplying both sides of the equation by that number will be to eliminate all the fractions and replace them with whole numbers. So the question is, what can I multiply by? Yeah. What can I multiply by to fractions? So Gabby says 70. I do not disagree. Helena said the reason that that number works is why. Where does that 70 come from?
Actually multiplying them all together.
Say again?
Multiplying them all together.
Multiplying, right. So multiplying all of the denominators together. So if we take all these denominators, 2, 7, and 5, and we just multiply all of them, we get 70. And 70 in this example happens to be, this is what Helena said, this is the least common multiple. Or you might think of it as a common denominator. If your job was to add these fractions together and you were looking for a common denominator, this is also the number that you would settle upon. Whoops. Least common multiple could also be used as a common denominator for all three of these fractions. So you can always get away in this technique with using just the product of all the denominators together. It may not always be the easiest choice, but in this case I think it also happens to be the easiest choice. So the technique says, let's multiply both sides of this equation by that number. Because this number is a multiple of 2, for example, when I multiply this fraction by 70, the fraction on the left, -3/2, what's going to happen? What happens when you multiply 70 by -3/2? Well, how do you multiply a fraction by a whole number? Yeah, make the whole number a fraction by using a denominator of 1, and then we can multiply across. Let me also propose a slightly different approach for multiplying these two fractions that might give you a little bit lower cognitive load when you're doing a problem like this. Remember that multiplication is commutative. So I can trade places when I multiply two numbers and end up with the same answer. Right? 5 times 12 is the same thing as 12 times 5. So since I know I'm going to be multiplying straight across in these two fractions, shouldn't I get the same answer if I decide, instead of multiplying the way that it's written, if I decide to flip-flop the numerators? Or I could also have flip-flopped the denominators. So instead of just straight up multiplying across, I'm going to instead trade the -3 and the 70. I'm just going to trade places with the two of them. So now I'm going to have -3 over 1 and 70 over 2. And I'm going to do this just because now the multiplication problem that I'm about to get is going to be a little bit simpler. Because I can do the 70 over 2 first. What is 70 over 2? And negative 3 over 1, well, that's a whole number. So rather than multiplying across and then reducing, we could always choose to flip-flop the numerators or flip-flop the denominators and just get a slightly simpler multiplication problem to do. But now I don't have to do any tricky reducing of fractions afterwards. Wait, that can't be right. My apologies. There we go. Of course, if we had just multiplied across and bit the bullet, we would end up with the same answer. It's just we would have written it as negative 210 divided by 2, and then reducing negative 210 over 2 would have given me negative 105. So whichever way you choose to do it, all roads lead to Rome on this. But the most important thing about this number is that it's no longer a fraction, which is good news for everybody, because by the time all the dust settles and we've multiplied everything else, those fractions will also have disappeared. Negative 2/7 times 70 over 1, and my u is right there, minus 9/5 times 70 over 1. I think here too, the process of deciding to flip-flop where the denominators are, where the numerators are, may make these multiplications a little bit simpler as well. So just for fun, I'm going to do that here as well. 70 over 1 times, 70 over 7 times negative 2 over 1, and 70 over 5 times 9 over 1. There's a u here, I've got a minus. And 70 over 7 is a nice number. 2 over 1 is a nice number. 70 over 5 is a nice number. 9 over 1 is a nice number. And then I have 10 times 2, and I think I lost a negative sign in here. Yeah, I sure did. And then 14 times 9. Uh-oh, what is 14 times 9? 132? No. 140 minus 9. Yeah, thank you. Wait.
No.
140 minus 14. There we go. 126. There we go. Yeah. Okay. Clearing denominators front loads all of your fraction hassle in a way that makes all the fractions go away, and now we can focus on the algebra that's necessary to get that u to be by itself. So how does that happen? What's the first step that we would do from here to begin to unwrap that u? Yeah, Derek.
I'm probably wrong on this, but you would, seeing how it's minus, you addition on
Okay.
both sides.
Okay, and what do I want to add on both sides?
20. 126.
All right, so let's think about which one it is and why. First of all, I completely agree that what we want to do first is we want to add, which, by the way, is a bit of an inversion of something. Usually, when we have two different operations going on inside of an expression, and we do on the right-hand side have both multiplication happening in between negative 20 and u, and then also subtraction happening between the minus 20u and the 126. So we have both a multiplication to worry about, and we also have a subtraction to worry about. But you're telling me that we want to deal with the subtraction first and the multiplication second? That doesn't sound typical. But it is typical when we're solving for a variable. Because after all, the order of operations tells us how to put an expression together. In the expression minus 20u minus 126, this multiplication on the u is going to happen first before this subtraction does. So if I'm u, the letter u, not the person u, if I'm u, then the first thing that's happening to me in this expression is I'm getting multiplied by 20, negative 20 rather, and then afterwards I'm subtracting 126. So u is kind of wrapped up in these two layers of wrapping paper in a way. So if I want to unwrap this present, I need to get at the u from the outside. I need to take this expression apart. But when you take an expression apart, you take it apart in the opposite order to that which it was put together. And so when isolating a variable, getting it by itself, the order of operations is to be used backwards. First, we'll do all the subtraction and addition that we can do to simplify, to get less stuff to be surrounding our variable on the right-hand side. Only after we've done all the subtraction or addition that we can do we worry about doing any multiplication or division. And once all that multiplication or division is done, then I suppose if there are exponents, we would worry about the exponents after that. And if there are parentheses, we would actually think outside in about parentheses instead of inside out. So we would work from outside of our parentheses towards the inside, if we had parentheses. So instead of PEMDAS, what we get is instead SADMEP. Worry about all your subtraction and addition first. Then once all that is gone, worry about your multiplication and division. And when all of that is done, worry about your exponents. And if you haven't wormed your way inside the parentheses, do that next. So this is how to isolate a variable. I like to think of it as unwrapping, which is what we're doing when we're solving an equation. Solving just means get that variable by itself, which is why we choose addition and subtraction first, and we choose it in a way that cancels out the place where subtraction is happening right here. So what we want to add to both sides is 126, because that's the step that's going to unwrap this outer layer of wrapping paper around my u that will undo my subtraction of 126 by adding to both sides 126. And so at the end of that process, I only have negative 20 times u on the right-hand side. And on the left-hand side, what's negative 105 plus 126? What'd you get? Yeah, when I do that, I get 21. So now all of our addition and subtraction is done. We don't have any more addition or subtraction present in our equation. So what's the last thing we need to do to get u by itself? Divided by negative 20. Divided by whatever u is being multiplied by. Here u is being multiplied by negative 20, so to get it by itself, I'm going to divide on both sides by negative 20. Another common source of error on problems like these is missing that minus sign when you do your final division. But that minus sign is there for a reason. So on the left-hand side, I'll get the number 21 over negative 20. And on the right-hand side, I'll have just u by itself. And now that the u is by itself, we know that we're looking at our final answer. We're looking at that value of u, which, if we were to plug that back into our original equation and evaluate, what should we expect would happen? If this is indeed the solution of our equation, what happens if I plug it back in?
You got more work.
Yeah, you got to do a bunch more work. But one of the best things you can do for yourself, in any course really, but in math in particular, I think, is to develop the habit and skill of knowing for yourself when you have a correct answer. And not always relying on an authority, like myself or like Ari or like any of our tutors. Don't rely on us to tell you whether you're right or wrong. Because if we tell you you're wrong on an exam, that costs you points. But if you figure out that you're wrong on an exam, you can fix it and get those points back before you hand it in. So that's what this step might do. If we plug that number back into our original equation, what do you think will happen? Left-hand side is still negative 3/2. Over here, if I multiply across, I'll get negative 42 over negative 140. I'll subtract 9/5. I'll have to do a bunch of fraction arithmetic on the right-hand side. And cancel these negatives. 42 over 140, I can reduce. I'm skipping some steps here just because I would like to kind of rush through this to get to the point. 42 over 140 is 1 over 30, 3 over 10. 3 over 10. And then if I place 9/5 into a denominator of 10, that'll be 18 over 10. And 3 minus 18 is negative 15. And negative 15 over 10 reduces to, dividing by 5, negative 3 over 2. Well, hey, look. If I plug that number back into my original equation, the result is an equation which has the same value on both sides. And that is exactly what it means for a number to be a solution of an equation. Being a solution means that when we plug it back into the original, we should have the same value on the left-hand side of that equation as we have on the right-hand side of that equation. This little check step, if you have the time to do it for yourself, you can rescue back a lot of missed credit. And you can really kind of take control of your understanding of whether you've done a question right or wrong.